So in this presentation, we're going to share some of our breakthrough research into zero-knowledge transcode verification. So all along the way we had done transcode verification was with the source and destination streams available for us to do an actual p-hash check on the source and the work and establish whether the transcode was right or wrong. So from there, we've come a long way and then made some breakthrough in the way we can actually scale up verification process and do more verifications on the blockchain without needing an off-blockchain verification node running all the time. So this research has been done by Ram and Taras, and they'll take us through in depth on their work. And this is very exciting for us as a product and as well as for the industry because zero-knowledge proofs, as of now, Zcash has been super successful in implementing zero-knowledge proofs for transactions. It's one of the most popular and stable implementations of ZK snarks out there. But nobody has really established and implemented ZK snarks for a high-throughput compute environment. And that's our attempt to establish ZK snarks for zero-knowledge proofs for a high-throughput compute environment like video. So I'll let Ram take away from here and explain what we've been doing.
Let's go to the the main motivation for looking at GK snarks or zero knowledge proofs in particular. Our current system needs a trusted verifier, whatever is there as part of alpha. You are looking at the ways to bring it back to on-chain verification. That's where we started adopting GK snarks and continuing research further on that. The main motivation is let the verifier run in a untested environment like normal blockchain transactions. And it also helps a very fast verification, even though it takes a lot of compute cycles to generate proof. The proof burden is passed to the miner. The verification will be very fast on the blockchain. So that results into very high scalability. Basically, each verification is supposed, based on GK snarks, is supposed to take less than 5 milliseconds. So that helps a lot in scalability. The next few slides will explain the major blocks of this GK snarks based proof. That basically contains moving our existing verification system to GK snarks. As part of it, we also come up with some challenges related to possibility of certain attacks. Taras is going to address how we are going to make it proof against those attacks. Next slide. So zero-knowledge proof basically contains 3 major blocks. One is generation of a proving key and verification key. This is a one-time task that needs to be done in a secured way. Otherwise, it may cause attacks. Once those keys are available, then there will be 2 kinds of inputs. One is the public input, where the client using the transcode system or VideoCoin will generate a public input that will be passed to the miner as well as to the verifier. The miner is supposed to generate a private input and supply to the proof system. The proof system basically validates whether the required work is done or not. So that will be explaining further in the next slides. But basic building block is a proof generation, which is being done by the miner, which is very compute intensive. That is where we are continuing to study how to tag it with the transcode process itself so that the miner won't be burdened. At the same time, the proof generation also decides how easy to attack the system, which we'll be addressing in the following slides. Next slide. So the proof generation basically, we currently are migrating from our current proof generation, which is a p-hash based. So instead of directly verifying the p-hash, we make use of elliptic curve cryptography to do a comparison using the homomorphic functions. So from this, you can hide actual p-hash values being used either at the verifier level or at the proof level. As part of proof generation, the miner is supposed to generate a p-hash and create its corresponding homomorphic function so that those values will be compared by the proof system. This basically helps hide the values applied by the client, as well as at the verification process, nobody can steal these values and reclaim as it is their work. So it will protect from that. So you also want to harden it by generating multiple p-hashes randomly selected from throughout the video segment, and also couple with SSIM, which is a structure similarity index between source stream and transported stream, that basically helps to certain extent prevent attacks like no-transcode attack that Taurus is going to discuss in detail. But this initial protection, we'll be elaborating more on this SSIM and make it very hard to generate fake proofs. So the private input is the result of transport process. It will generate p-hashes and SSIM, which will be compared by the proofing system, and it generates the proof which will be supplied to the verifier. Let's go to the next. The verification process is very straightforward. Here, there is no knowledge of how the proof is generated or what it is verifying also, thanks to the homomorphic functions being used by GK snarks. Ethereum kind of blockchains also support this verification in the form of precompiled contracts, which basically makes it make it as part of normal blockchain operation, and issues related to gas consumption won't arise. So here we repeated all the steps that we indicated previously in the bigger picture of the whole transporting process. The idea is the GK-SNARK's proof generation system seamlessly plugins with the current alpha without causing any reshuffle. From that point of view, the proof generation and verification merge smoothly with our current alpha system. Let's go. From this slide onwards, Taurus is going to take over and explain what kind of attacks we anticipate and what we are trying to do by enhancing our GK-SNARK's implementation further. Taurus, can you take over?
Okay, thank you. So current transcode verification process, which was like described previously, has like one vulnerability. It's like call it no-transcode attack, which basically means that miner can generate a proof based on source stream instead of transcoded stream, and it means that basically miner can get the reward without doing any actual transcoding operations. So in order to fix this, we have to add transcoding operations into verification process. Okay, next. So for that, we have to add macro block decoding computations into verification system. So here we have this process divided in 3 parts. where, for example, client has to decode macro block from his input stream, generate a structure similarity index from it, and send it to verifier. The same things should be done on a miner side, but with additional step where miner has to generate a proof where the actual macro block decoding operation was executed. And this proof has to be sent also to verifier. And verifier is only required to compare those similar structure similarity indexes, and also to check the proof received from the miner. Okay. Next, so one of the way how to implement this is to use TinyRAM architecture. So what is TinyRAM? Basically, it's a random access machine which provides correct execution verification for any programs written in high-level languages, for example, in C language. So in order to get zk-SNARKs proof from any computational algorithm, in our case is macro block decoding algorithm, we have to go through a few steps. First of all, we need to generate a TinyRAM program, which is basically an assembly code, which is very similar to x86 architecture, computer architecture. So for that, we have to use a TinyRAM compiler, which will generate those assembly code program. So, and we also have to use a circuit generator, which basically will use this assembly code as an input parameters in order to generate circuits. And when we have the circuits ready, we will be able to generate proofs from it, which will be sent to verifier. So, and next. So as a result, we have like straightforward, one of the straightforward benefits is we are able to embed transcoding computations into verification process. And also with use of TinyRAM architecture, we are able to provide new enhancements algorithms if they will be needed in future. But also with benefits, we also have challenges, such as like difficulties in implementing such architecture, because such implementation of TinyRAM is like relatively new, and there is not a lot of like practical studies how to work with it. And also we have a lot of like lack of tool chain or instruments to work with that. One of them is like lack of compiler, TinyRAM compiler, where we need to translate, for example, high-level language like C into assembly code. And basically that's all.
Great. So yeah, thanks a lot, Taras and Ram. I think the overall summary here is by doing zk-SNARKs and taking off the verifier node from being an off-chain operation and into an on-chain operation helps us scale the verification process tremendously. So right now, sometimes it takes 60 to 70 milliseconds to verify every proof that comes in. This can bring it all the way down to 5 milliseconds. Now that comes with a bunch of challenges that that we're trying to address through our research and development. Is one is obviously this is extremely hard to implement because nobody has done this before, and zk-SNARKs have been successful only in really small text transactions where the circuit to generate the SNARKs are fairly straightforward to, have been proven and have been implemented, and research has been done. So for us to implement the zk-SNARK circuitry for something as complex as video encoding and decoding is extremely hard. But we made a lot of progress, and and our research is showing a lot of promise. And we believe that with our same alpha architecture protocol, that we'll be getting into depth into in one of the protocol demo videos, we can in fact take off the verifier, which is an off-chain activity, and then bring it on-chain, thanks to the research that we're doing here. So that's the that's the presentation and demo here. And please keep in touch with us over our Telegram channels, and also follow our Medium posts for the upcoming more alpha demos and releases. Thank you so much for joining us.